We've generally been introduced to integrals and like the basic notation and definitions. It's about time that we actually learn what accumulation of change really is, so what it really means. And we're going to do that by actually looking at accumulation of change in context, right? And so we have over here two word problems. We're going to start with this one. So a car drives for a period of 6 hours. The speed of the car in miles per hour as a function of time in hours is graphed below. How far did the car travel in the 6 hours? So we're looking at the distance covered, so how far did the car travel in those 6 hours, so over that entire 6 hour time period. So here we have the function graphed over here, right? We're given the velocity as a function of time, right? And they're basically asking us how much distance did this car accumulate over time, right? So how much distance did this car travel is another way of saying just how much distance did this car accumulate over time. And so we can kind of see the correlation to the general notion of accumulation of change. And so the way that we would write this problem out, if we wanted to write it like in terms of an integral, is we want to figure out the accumulation of change from time t equals 0 to time t equals 6, right? We're trying to figure out over this entire time period, I'm going to highlight over here, this entire time period, how much change did this function accumulate, right? So what we're going to try to do is we're going to try to find the area under this curve in order to determine the accumulation of change of this function. And the area under the curve is, as we said previously, the integral. And that's a pretty ugly integral sign. Let me fix that. It's going to be the integral from t equals 0 to t equals 6 of v of t. And then what are we integrating with respect to? So what's going to be our differential? Well, here our independent variable is t, so we're integrating with respect to t, so we'd write dt. So let's just go ahead and analyze this kind of for a second. I'm just writing this out so we can get a little bit more comfortable using integral notation. So here we have our lower bound, which is time t equals 0, and here we have our upper bound t equals 6, right? Because we're trying to figure out how far the car traveled within that 6-hour time period. And then here we have our integrand v of t, right? We're trying to integrate the velocity. We're trying to find the area under the velocity curve in order to determine the accumulation of distance, or the accumulation of, really just distance, displacement, whatever you want to say. And then here we have dt, right? We're integrating with respect to t because in this case, t is our independent variable and it's the variable that we want to integrate with respect to, right? And so now that we've gotten the notation out of the way, let's see how we can actually evaluate this graphically. So what we're going to try to do is we're trying to find this entire area under this curve over here. So let me actually erase that now. And the way we can do it is we can actually go ahead and divide this up into different smaller areas, right? And so we can divide it into maybe this area over here, this area over here. And if you aren't really comfortable using the trapezoid formula for area, you can just go ahead and divide this one as well. I'm going to be honest, I hardly use the trapezoid area formula, so we're just going to ignore that. But you could also use that. There are many different ways to approach this. And essentially what we're going to do is we're going to find each individual area and just add all of these up in order to get the total area under the curve, right? This is just a very simple geometric method when you're given a simple curve in order to get, in order to evaluate integrals, right? Evaluate definite integrals, I should say. So this first area over here, from time t equals 0 to t equals 3, it looks as though we have kind of a square, or not really a square, but rather a rectangular shape over here, right? So the base is 3, and the height looks to be 40, right? And so we know that this area, I'm going to call this A1, we could say, is going to be 3 times 40, right? Because we know that the area is just going to be given by the base times height, or the length times width, whatever you want to say, which is going to be equal to 120. We don't really care about the unit at this moment, actually. So this right over here is going to be 120 units squared, whatever. And then over here, right, here we have, well, actually, technically here the units would be in miles, right? So miles. And so over here now, for this little square, it looks like the base is from 3 to 4, right? For t equals 3 to 4, so the base is just 1, right? 4 minus 3 is 1, and the height is 20, so 1 times 20 is going to give us 20 meters, right? And then for this little triangle over here, we're going to use the formula 1/2 base times height. The base is again 1, the height looks to be 20 as well, and so we're going to end up with 1/2 of 20, which is 10. So this, let me just this is going to be 10 meters, or miles rather. And then finally, this last little piece of area over here, from 4 to 6, from t equals 4 to t equals 6, again, we have a height of 20 and a base of 2 this time. And so 2 times 20 is 40, and we end up with each individual area. So the total area, right, is going to be equal to 120. It's just going to be the sum of all these individual areas, right? So 120 plus 10 plus 20 plus 40, right? We got that from each individual area. And so 120 plus, what is this? 170 plus 120, or 170 plus 20, that's 190. Did I do that right? 160 plus 10 is 170 plus 20. Okay, perfect. So 120 miles. So the car traveled 190 miles over the 6-hour period. So I know these are very strange numbers, whatever, but let's just suppose it works out. So 190 miles over the 6-hour period. So next we have a bucket with a hole punctured in it, which releases water for 10 minutes, so over a 10-minute time period, until it empties completely. The rate of the flow of water out of the bucket in liters per minute as a function of time in minutes is graphed below. How much water was lost in between 5 to 7 minutes? So we're basically just looking, so here we're given the rate of flow of water out of the bucket, and what we're trying to find is essentially just how much water flowed out of the bucket within a certain time period, between 5 to 7 minutes, right? So essentially what we're trying to do is we're trying to figure out the accumulation of change of the, I suppose you could say, rate of change of this bucket over the period from 5 to 7 minutes. So we're just trying to figure out how much water flowed out of this bucket within 5 to 7 minutes, right? And so here we have r of t, and we have t as the independent variable. So if we wanted to write this as an integral, then we would go ahead and say that this is going to be the integral, this time from 5 to 7, right? Because we're looking between the time period of 5 to 7 minutes, of r of t. And again, we're going to use dt as our variable of integration, as our differential, because we're integrating with respect to t as our independent variable. Again, if we want to analyze this notation, the integral tells us we're looking at the accumulation of change, or rather the definite integral tells us that. And then the two bounds of integration, 5 to 7, basically just tell us the time period we're looking at. We're looking at 5 to 7 minutes. R of t is the function we're integrating, which is the rate of flow of water out of the bucket as a function of time. And then this dt over here just tells us that we're integrating with respect to time. So time is what we call our variable of integration, or t is our variable of integration. And it essentially is just telling us in this case that it's our independent variable we're integrating with respect to time. And so if we're to look at this graph over here, we're looking between 5 to 7 minutes. So if we were to draw a straight line like that, and then another straight line like that, to get from 5 to 7 minutes, then we have actually a very simple area problem, right? This is just going to be a rectangle. So the base is going to be from 5 to 7, so the base is going to be a length of 2. And then the height, if we were to check the value of this function, it would be about 6 at this point. And so we can say that the height is going to be 6. So 6 times 2, that gives us our entire area, which is going to be 12, right? 12 liters. So this evaluates simply to 12 liters, and that would be our final answer. We would say that 12 liters, or the bucket lost 12 liters between 5 to 7 minutes. And so that's essentially accumulation of change for you, at least graphically. I definitely recommend you try different graphical problems with accumulation of change and practice writing them in integral form so you get more comfortable using integrals or definite integrals to represent these sorts of accumulation of change problems.